Swayam Prabha. Digital India. Educated India.
Next, we are going to look at shear stresses in thin wall sections. Okay. So, till now we have been looking at shear stresses in thick wall sections. So, now we look at shear stress in thin walled sections. Okay. So, now let us look at this I section which is thin walled, which is subjected to some bending moment, okay, varying bending moment along the axis of the beam. Okay. Then what happens is I have this I section which is subject to varying bending moment along the axis of the beam. So, there will be a shear force also in the sections. Okay. Now, let me cut this I section using a plane as shown there. Now, if I cut that, what happens is I expose this surface. Now, for this section to be in equilibrium which is of length delta x, I have a compressive stress of sigma xx coming at this face, and there is a stress of sigma xx plus dou sigma xx by dou x into delta x on this surface. Okay. So, this stress is more than this stress. So, there should be a shear stress acting along the cut surface in this direction. Okay. And hence there should be a complementary shear coming acting on this flange in this direction on this side of the web. Okay. This is a complementary shear, this is the actual shear stress that is acting on this section to maintain equilibrium. Okay. Now, to compute this shear stress, the expression remains the same, it is Vq by Ib, except that now the B would be the thickness of this flange. Okay. And your area that you have to consider should be taken from this end to the section point where you are interested in finding the shear stress. Okay. So, you have to take the entire flange thickness area rather than sectioning the flange along a plane which is cut along the parallel to the xz plane. Okay. Now, you are cutting a plane parallel to the yz plane. Okay. That is, you are cutting a plane like this and not horizontally, you are having a vertical plane of cut rather than horizontal plane of cut. Okay. Another point to understand here is at the bottom flange you have tensile stresses coming in here. So, if this tensile stress is more than the tensile stress acting on the other surface, acting on this surface, that the shear stress should act like this along this direction rather than the direction that it was acting in the top flange. Okay. And then the complementary shear would act like this rather than in the direction that is shown in the top flange, rather than the direction that it was acting in the top flange. Okay. And hence if you see together the sigma xz stress, that is a flow, like from here it comes here, transforms into sigma xy and then flows on to sigma xz there. Similarly, it comes here, goes to sigma xy and becomes sigma xz there. Okay. So, this is called as a shear flow in thin walled sections. Okay. Basically, the shear stresses arise to maintain equilibrium of the sections when there is a varying bending moment. Okay. It is not necessary that always this varying bending moment should produce only sigma xy shear stress, you can produce even sigma xz shear stress, okay, as we see here. Okay. But the expression to compute these shear stresses are the same. Okay. So, now let us go ahead and compute the shear stress distribution for this I section. Okay. As before, let us assume that the thickness of the flange is, let us assume that the thickness of the flange is Tf, and the depth of the web is H, Tf, the thickness of the web is Tw, the width of the flange is Bf, both top and bottom, the same with Bf. Okay. Now, to compute the stress sigma xz, I have to cut a plane. Let me cut a plane like this. Okay. Now, the area that I have to look up here is this area to compute the shear stress at that location. Okay. So, what is that area? That area would be, let us assume that I am measuring S from this end, that is locating the section from the left extreme of the flange. Okay. So, I have sigma xz given by Vy by Izz by B now is the thickness of the flange Tf, okay, and the area would be S into Tf, okay, into the center of that area. The center of this area is somewhere here, that will be H by 2 plus Tf by 2, right. Okay. So, this becomes Vy by Izz into H plus Tf into S by 2. Okay. So, now what happens when S is 0, the shear stress is 0 as it should be, because I am not applying any shear on the outer surface of the flange, okay, and hence the variation of the shear stress along the flange is going to be something like this. It is going to be something like this. It varies from 0, varies linearly up to there. When H is Bf by 2, I will have the maximum shear stress, which is sigma xz max at S equal to Bf by 2 is tau 1, which is Vy by Izz into Bf into H plus Tf by 4. Okay. So, that will be tau 1 there, and on this surface you can continue S because the direction is changing. Okay. So, what happens is this will decrease like this. Again I have to take a S from this section, I have to take a S from this section, move on here, this will become S2, okay, and I have to compute the variation like that. Okay. Now, how do you assume this S is a question? You have to assume S such that it is for the along the same direction as the shear flow. Okay. Now, same direction or opposite to the direction of the shear flow, but it cannot cross, it cannot be continuous across sections where the shear flow changes its direction. Okay. It should be against the shear flow direction or in the shear flow direction. Okay. In both these cases I am assuming it to be against the shear flow direction, okay, but I can't go from against the shear flow direction to a direction where it is along the shear flow direction. Okay. So, that will be the variation of tau sigma xy on the top flange. A similar expression will obtain for the bottom flange also. So, the bottom flange also there will be a variation which is like this. It is the same thing as we saw for the thick wall sections, and this will be tau 1, this value is going to be tau 1. Okay. Now, let us see what happens in the web. Okay. Now, we are interested in finding what is the variation in the web. The variation in the web is similar to what we had for a thick walled cross section. Okay. So, since it is similar to a thick walled cross section, you will have sigma xy is that direction of that shear stress, okay, that is again given by Vy by Izz into Ys into As divided by the thickness of the web, because that is the B, okay. And when I am looking at the web, I have to consider the entire flange area and a portion of the web area, okay. That is similar to the expression that we obtained here, it is similar to the expression that we obtained here for the web, right. The same area I have to consider for the web, hence the equations will remain similar as what we obtained here, okay. So, let us go ahead and plot that resulting equation. So, what happens, it at the web flange interface there is some shear stress which is non-zero, okay, and then at the neutral axis location is where the maximum shear stress occurs, okay, and that maximum shear stress is same as what we had before, okay. This will be nothing but as we saw here, that will be Vy by Izz into Tf Bf by Tw into Tf into H plus Tf by 2 is going to be Izz into Bf by Tw H plus Tf by 2. Into Tf, okay, and the maximum shear stress is going to be, and this is tau max, that is going to be Vy by Izz into Bf by Tw into H plus Tf by 2 into Tf plus H square by 4, okay. Okay. So, that is going to be your tau max, same as before, okay. So, now let us understand where this variation in the shear stress profiles is important, okay.